Hey everyone. So, if you're a software engineering student, you've definitely been here. You've got this amazing design on a whiteboard, this perfect architectural blueprint, and then you stare at it and think, okay, now I have to actually build it. Today we're going to break down that exact process, how to turn that high-level design into clean working code. Let's dive in.
So here's what we're covering. First, we'll talk about that big challenge, turning a vision into reality. Then we'll get into the practical stuff, a step-by-step map for going from design to code. After that, we'll explore interfaces and why they're like contracts for your code. And finally, because things always go wrong, we'll look at how to build code that can handle errors like a champ.
All right, let's jump right into our first section, from blueprint to code. This is really the foundation. It's where we tackle one of the biggest hurdles in software development, taking that perfect idea and translating it into the, messy reality of actual code.
So just picture this for a second. You spent hours, maybe days, with your team. You've sketched out these beautiful class diagrams, the interactions are perfect, the whole thing is a work of art up on that whiteboard. And then you step back, and that big question hits you. Okay, now what? How do we actually build that thing?
Well, at the end of the day, coding is the goal, right? A design is just the plan. The implementation, the code, is the actual construction. And you got to remember, this isn't some one-and-done thing. It's always iterative. You build a little piece, you test it, you make it better, you build the next piece. All the time, you're getting closer and closer to that original vision from the blueprint.
Okay, so how do we do that in a smart way? That brings us to our next section, and this is kind of the core of our explainer today, the design to code map. We're going to lay out a really practical, step-by-step approach for translating your design directly into good, object-oriented code.
A really popular strategy is what you could call the sketch and code approach. It's super simple, just 3 steps. First, you start with your design, your class diagrams. Then, for each class in your design, you create what's called a head class in your code. You can think of this as the manager. Its only job is to coordinate things. Finally, you create smaller specialized helper classes to handle the actual tasks. These are the experts that the manager delegates all the work to. This is so cool because it keeps your main classes super clean and your whole code base way more organized.
And here's the best part, especially if you're using a language like Java. The mapping from your design to your code is surprisingly direct. Your class diagrams, they literally become your class definitions. That's the skeleton of your app. Those interaction diagrams you drew, that's the logic that goes inside your methods, the muscle that actually makes stuff happen. The attributes you listed are now your class variables, and the methods become your functions. It's a really clean one-to-one translation from blueprint to code.
All right, now let's talk about a really powerful tool for keeping your designs clean: interfaces. The best way to think about these is as official contracts that define how all the different parts of your code are allowed to interact with each other.
So yeah, an interface is basically a formal contract. It lists a set of methods that a class has to implement if it agrees to the contract. This is a perfect example of abstraction. It lets you focus on what an object needs to do, its actions, without worrying about how it does it. That separation is absolutely key for building flexible software that's easy to change later.
In this contract, it's got some really strict rules. An interface just declares methods. You can't put any implementation code in there. Every single one of those methods has to be public, so other parts of the program can access them. And last, you can't declare any variables inside an interface. It is purely about defining behavior, nothing else.
Okay, so we've mapped our design, we've written our code, we've set up our contracts with interfaces, everything is perfect, right? Well, no. In the real world, stuff breaks. So let's talk about what happens when things go wrong, and how we can get ready for it, because it's going to happen.
And that's where this key term comes in: exception. An exception is just a condition that's caused by an error while your program is running. Think of it as your program throwing up its hands and waving a red flag, saying, hey, something just happened that I was not expecting.
And these errors can pop up from anywhere, right? It could be a user typing in nonsense. It could be a file that your program needs, but it's just gone. Maybe the network connection drops in the middle of a download, or a piece of hardware just fails. These are all real-world problems our code needs to be ready for.
And that brings us to our final section, handling the unexpected. This isn't just about squashing bugs. It's really about adopting a professional mindset. It's about building software that is resilient, that's robust, and that doesn't just fall over and die the second the world isn't perfect.
So, the standard way to handle exceptions has 3 key parts: try, throw, and catch. First, you put any risky code, anything that might fail, inside a try block. If an error does happen in there, the system throws an exception object, which kind of pauses everything, and that's when your catch block, which is like your safety net, catches that object so you can handle the error gracefully and let the program carry on.
Now, it's useful to know there are two main types of exceptions. A checked exception is for stuff that's totally out of your control, things you can't possibly predict, like the user deleting a file while your program is running. The compiler actually forces you to handle these. Then there's a runtime exception. This one is usually your fault, a bug in your code, like trying to use an object that's null. The compiler just assumes you should have written better code, so it doesn't make you handle it.
What's really powerful is that you can also create your own custom exceptions for problems that are unique to your app. So, why would you do this? Well, imagine you're building a login system. You could create an invalid password exception that you throw whenever someone types in the wrong password. To do that, your custom exception just has to inherit from the throwable class. You'll extend exception for a checked one or runtime exception for a runtime one. It gives you so much more control over how your program handles errors.
So I'll just leave you with this one final thought. What do you think is more important in professional software engineering? Writing code that works perfectly, but only under ideal conditions? Or writing code that fails gracefully and predictably when it gets hit by the messy real world? It's a question that really gets to the heart of what building great software is all about. Thanks for watching.